Hi, welcome back to ESP14 Presents. My name is Mark. When I got my first computer, all I needed was two outlets, one for the monitor and one for the mainframe. Over time, I extended my laboratory, my computer, by including a printer, a label printer, a scanner, a CD player, a MIDI controller, another printer. Sometimes I like to use a charger, and the list goes on and on. And by now I have an office with a whole load of outlet sockets, I think more than 12, and each socket is occupied with one of these annoying power adapters. So I decided there must be a better way. So I decided to design a power distribution block. And not only does it distribute power from one main power supply into several individual powers, it also includes an energy monitor. So now I can monitor exactly how much energy each device is using, and I can see how much it will cost on a yearly basis. So I'm going to build a power distribution monitor. Okay, so let me walk you through the schematic. Let's start with the microcontroller. It's an ESP32. We have a display. We have some output LEDs to indicate which output is enabled. We have our power section. It has two regulators to create a 5 volts and one that we can set, and it has a 12 volt output. And the one we can set is because some outputs are not 12 volt, but they have to be like 8 or for some occasions 7 or maybe 5, and you can regulate that using a trim potentiometer. Then we have a rotary encoder that I will use to program the user interface with, which brings me to the sections. It's 8 of them and they're all the same. So let's pick one. We have our energy monitor. And we have some outputs that can be enabled or disabled using the input from the microcontroller. And basically that's it. So we have 8 outputs that we can monitor and then enable and disable it by the microcontroller. So let's start building. Okay, so this is the power board, and as you can see, most surface mounted devices, the small components already have been installed. That was done by my manufacturer on my request, so I don't have to do it. All I need to do is add the energy monitors and all the through-hole components. On this board you see the potentiometer here, or the trim potentiometer, that is used to adjust the power output for some outputs. Then we will install the microcontroller here. The rotary encoder will be installed here. We have a display that will be installed here. And then of course we have all these output connectors, power connectors, that will be installed all the way down there. Okay, so let's use the microscope to get started. Well, by now you know how I work. First I always do one pin with soldering tin, and then I solder the rest. Start with 4 of them. Okay, those are the first 4, and now I'm going to solder the remaining pins. Okay, so 4 more. That's not good. Yep, that's why I use a microscope, so when I screw up I instantly see it and I can correct it before smoke gets in your eyes. Okay, so it's time for the through-hole components. We have our power connectors, a display with the header, the ESP with the headers, 2 capacitors, and a rotary encoder. So we're going to fix that next, and then the soldering is done. So let me install this first, so it's easier to have them in the right place. That should be there. Yep. So that's a microcontroller. Next is our display connector. Next is the rotary encoder, and we might as well install the 2 capacitors. Okay, so let's start assembling everything to one nice device. I made a 3D printed housing that I designed. I will include the files, of course, so you can print it yourself. First thing first, let's assemble the PCB. That will go right in here. And then I will screw that down with 3 little screws. Then this one will go on here and the button will go there. But first I need to install the LEDs. I think this is going to work out just fine. Okay, so I placed all the LEDs on the PCB and I checked the distance towards the lid to see they have the right height for mounting. And now I'm just going to solder 1 wire of each LED, so I can still adjust the placement a bit later if needed. Okay, so now let me check the lid again to see if the alignment is still okay. And then I notice that there's a little LED that needs some adjustment. So now I just solder the second side of the LED, the second wire, sorry. Okay, so the LEDs are in place. I checked the alignment with the lid, everything's fine. And basically it's almost finished. But there are 2 more important components I need to add. One will be the turning knob that goes on here, but another one, and that's quite important, that's a heatsink. Okay, so as a heatsink I designed my own. I will include the step file for you to reproduce it, but basically another heatsink that will fit might do the job just fine. It all depends on how much power you're going to export. So this will be mounted right here, like so. But since I cannot screw it, I'm going to use thermal glue. And this is a special glue designed for gluing heatsinks to components. It says heatsink plaster, which basically means heatsink glue. Okay. That works just fine. A little dot here, a little dot there. That will do the job. There's a difference between this one and actual thermal paste, because thermal paste doesn't stick. It is a bit sticky, but it doesn't glue down the components. But this one does. I do need to make sure that the glue has dried before I apply some real power to the unit, because too much heat will melt the glue again if it's not already hardened. So I'll just let this wait for a day and then I'll continue. Okay, so when you open the sketch, you'll see two files. We have powerhop.eno and we have element14splash.h. If you only see one file, that means in your directory one file is missing and you have to copy them manually. Both files are needed for this to work. Let's focus on the powerhop.eno because that's the main file. The other one is just some binary file to show a graphic illustration on boot up. So let's focus on the powerhop. And first we see the header, which has some general information of what to expect. Individual channel switching, adjustable current limiting, automatic overcurrent protection, and so on. Most important, I put the libraries here that have been used and the version numbers. So if something doesn't compile on your end, you can always upgrade or downgrade to this appropriate version numbers for each library, and then it should run just fine. Well, I'm not going to walk through all of it, but I will just show you. We have some configuration, we have some pins for the display, the encoder, the power chips, and what I'm actually looking for is my forward declaration of functions. Here you see a forward declaration of each and every function that's used in this program with a little comment of what it does. And this might help you debug, and the functions itself are at the bottom of the file. You can just find it there, but at least now you have an overview of all the functions that are here and what they do. Of course, first we have a setup in which we initialize some stuff like the display, the rotary encoder, the sensors, the outputs, and we retrieve some parameters from the non-volatile memory in which the used energy has been stored, the channels that were on or off last time, and a few more things. And then in the main loop, basically all we do is monitor. We monitor flag events, like was the rotary encoder used, was it turned left, was it turned right, did someone press the button, and if they did, then we have to anticipate appropriately depending on what layer in the menu we are in. The screen will be updated with the appropriate info, and we can change the parameters that are shown on the display, like maximum current, channels on off, the screen you see, and that's basically all it does. Oh, one very important function there is, we have a periodically check for overcurrent. Each and every channel is monitored, and it's compared to this maximum set current that you can change in the menu, and whenever that current is exceeded, something is triggered and the output will be disabled immediately. That way we can protect the system from overloading. And then you have to manually enable a channel again by using the menu. And then of course we have some energy monitoring, and we store that in a non-volatile memory, and that's all there is to it. Yeah, then we have our functions, but I suggest you go through them one by one yourself. Most important, if you want to program a do-it devkit1 board, you first have to make sure that the board manager has your board. For that you go to preferences, and you add the additional board managers links, and this one is important. That's what you need to add to be able to see the expressive ESP32 boards. And once that is done, you go to the board manager and then you type ESP32 and you pick the expressive systems, not the Arduino. The ESP32 expressive system you install. I have version 2017 installed. There is a higher version, a newer version, you can try that as well. But I used the 2017. You install it, and then all you need to do is select the right board here. Do it devkit version 1. Okay. And then you press upload or compile and upload. But I know my file is already working, so I continue with compile and upload, and then it will compile and upload to the ESP32, and that's all there is to it. Okay, when you switch it on, the first thing you notice is the display. It has a nice some dots, and it says green and channel 4 blue, which means channel 4 is blue. It was turned off manually. If it's triggered, it will be red or orange. And by triggered, I mean when it has an overcurrent, because for each channel you can set the current. And right now, channel 4 is set to a limit of 0.7. Let me switch on the channel again. Now it's on. And we go back. And in the display we see the current right now is consuming 0.15 amps. We can also see the voltage. Channel 4 has 9.05 volts and 0.13 amps. We can also monitor energy that's been used, and since I've been using this device on channel 4, I used 0.02 kilowatt hours, which is equal to €1, because I set the unity price very high for test purpose. It says €1 per kilowatt, which is extremely high, but it fits the purpose right now. You can change that amount, of course. Then when I go back to this one, there's a current limit, and I will show you. The minute I set the current limit for channel 4 and I'll set it lower, then at some point it will detect and it will switch off, and you can see that by the LED going off. Current. Now watch closely. Bam. Now it turns off. The LED goes off, and in the main menu it will also show you something. Let me just wait. It will go back automatically, so we test that as well. You see it's a red dot, which means it has been triggered. And now I manually have to enable it again. It says triggered or tripped, and I enable it. Of course it goes off automatically because the load is still attached and I didn't change the current. So let me change that again. Okay. And now I can switch it on. Simple as that. This is all I have for you today. I hope you enjoyed it. Remember, we have the Element 40 community, and for this project there is also a project page where I will upload all the schematics, the source coding, the housing, the heatsink, well, you name it, everything you need to rebuild this device yourself. And you can leave comments. If you're going to change something, please let me know. I'm very curious on what you're going to change and why. And of course, if you have questions, feel free to ask them in the community, and I'll do my best to answer each and every one of you. While I am going to install this on my computer, I'm going to think of some new projects that we can do in the next video. Until then, I see you next time.